If you've spent any time with Java, you have definitely run into the ArrayList. I mean, it's a total workhorse, a real powerhouse data structure. But do you actually know what's going on under the hood? Like, really know? Well, that's exactly what we're going to break down today.
Just think about that for a second. Regular arrays, they're fast, they're powerful, but man, are they rigid. You have to lock in their size right at the beginning, and that's it, you're stuck. It's a classic headache. But what if you could get all that array goodness without that one massive limitation?
Well, that's it. That's the magic trick. That is exactly what an ArrayList brings to the table. In this explainer, we're going to dive into how it pulls this off, why it's pretty much the default choice for so many developers, and, this is crucial, the performance trade-offs you absolutely have to be aware of. So, let's get into it. All right, first things first, what exactly is this dynamic array solution that saves the day? It's time to properly meet the ArrayList.
You know, the official definition here really nails it. It's part of the list interface, so you know it's an ordered collection of things. But the key phrase, the magic word, is resizable. It gives you the raw speed of an array with the wonderful flexibility of a list that can just change its size whenever you need it to.
And you can see how simple this is right in the code. We just declare a new array list, and we start adding stuff. See what's missing? There's no number, no fixed size we have to commit to. The array list is just handling all of that messy business for us. But how? What's the secret sauce? To really get it, we've got to pop the hood open and take a look at the clever mechanics that make all of this possible.
And there it is, the big secret. An ArrayList isn't some brand new space-age data structure. It's actually just a smart wrapper built around a plain old fixed-size array. It's just managing that internal array behind the scenes, so you don't have to.
So what happens when you try to add one more item and that hidden array is already full? Well, it kicks off this little four-step dance. First, it creates a brand new, bigger array, usually 1.5 times the size of the old one. Then, it painstakingly copies every single element from the old array over to the new one. And finally, then it adds your new element. It's simple, but it's incredibly effective.
And this whole process introduces two really important concepts, size and capacity. Size is easy. That's just how many things are actually in your list right now. You get it with list.size. Capacity, on the other hand, is the total number of slots in that hidden internal array. It's how many items you can have before it's forced to do that resizing dance again. The one thing to always remember is that your size is always less than or equal to the capacity.
Now, you might be thinking, creating a whole new array and copying every single element over, that sounds kind of expensive. And you'd be right. This flexibility doesn't come for free. It comes with some really important performance trade-offs. Which naturally leads us to this critical question. With all this resizing and copying potentially happening in the background, is adding an element to an array list always a fast operation?
The answer? A classic, it depends. And it all depends on where you're adding that element. Sticking something on the end, super fast. Most of the time there's an empty slot waiting. We call this an amortized constant time, or O1 operation. But trying to wedge an element into the middle? That's a completely different story. To make room, you have to shift every single element after it one spot to the right. That's a linear time, or ON operation, and it gets slower and slower the bigger your list is. Just look at this line of code. We're adding Zo at index 1. Seems harmless, right? But if that list already has 1 million items in it, this one simple line forces the computer to move 999,999 other items. That is a potentially huge performance hit, and it's something you've always got to keep in the back of your mind. And this table really puts it all into perspective. Look at where ArrayList just absolutely shines. Getting an element by its index, O of 1, blazing fast. Adding to the end, also O of 1 on average. But look at inserting at the beginning. That's our worst-case O of n scenario. And, well, that's where you might start looking at something else, like a linked list, which is designed to be amazing at exactly that. Okay, so now that we know its strengths and its weaknesses, how do we use an array list the smart way? How do we get all that performance without the pain? It's actually pretty simple. You play to its strengths. If you need to grab elements by their index all the time, what we call random access, ArrayList is your undisputed champion. If your application mostly just adds new things to the end of the list, it's going to be incredibly efficient. And as we'll see in a moment, if memory usage is a big deal for you, ArrayList is a very lean choice. All right, here's a fantastic pro tip for you. If you have a pretty good idea of how many elements you're going to end up adding, you can give the ArrayList a little heads up and save yourself from all of those expensive resizing operations.
You can do this with a cool little method called ensureCapacity. So in this example, instead of starting with a default tiny capacity and then resizing again and again and again as we add items, we're basically saying, hey, listen up. We're going to need room for 10,000 integers, so just go ahead and allocate all that memory for me right now. This one line of code can give you a massive performance boost when you're doing bulk adds.
And there's another, more subtle reason why ArrayList is so fast, especially for iteration. Because it's all backed by an array, the elements are stored right next to each other in memory. They're contiguous. This is a huge deal for modern CPUs. When a CPU asks for one element, it's smart enough to say, hey, I'll probably need the next few as well, and it loads them into its super fast cache automatically. This makes looping through an array list surprisingly zippy.
But of course, there's no silver bullet in programming. No data structure is perfect for every single situation. So it's just as important to know when an array list is the wrong tool for the job.
But first, let's look at one more area where ArrayList is the clear winner: memory. Just look at these numbers. For the same 1,000 elements, a linked list can take up almost 5 times more memory. That's because of all the extra overhead it needs. So if you're working in a memory-sensitive environment, ArrayList is a no-brainer.
And that really brings us to the main takeaway. For most general-purpose list needs, ArrayList should be your default choice. It's fast, it's memory efficient, it's versatile. Its one true kryptonite, its real weakness, is when you need to constantly add or remove things from the front of the list, like you would in a stack or a queue. That ON cost for shifting all the elements will absolutely crush your performance.
So that leaves us with one final hanging question. If ArrayList is so terrible for operations at the front of the list, what are you supposed to use instead? What data structure is built from the ground up to make those exact operations lightning fast? Well, that's a story for our next explainer.